Well, in 1964, as you see there, Arno, Penzias, and I had been working about a year putting together a precision measuring system to work with the 20-foot Horn-Reflector for several measurements that we wanted to make. And this measurement that I'm showing you here was the first one that we made in which we had the whole whole equipment together, and it immediately showed a problem. At that point, what we saw was that the antenna had almost twice as much noise as it was supposed to. It was hotter than the liquid helium rather than colder, and clearly this was a problem. It was a disappointment. In retrospect, this messy looking record shows the most important thing that I ever measured. It's the first evidence we had for the cosmic background radiation. In this talk, I'd like to discuss how we got to this point, the source of the excess how the source of the excess noise was identified, and in the end, maybe a little retrospective about what it feels like to look back on it. I went to Caltech as a graduate student in 1957, and during my first semester there, Sputnik was launched. I knew this was an important event, but I didn't realize how important it was going to be for me. In the third quarter of the year, I had to join some research group to do a little bit instead of having a course, and I joined a new radio astronomy group. They had just completed the heavy construction for the Owens Valley Interferometer, and were about to build receivers and start making observations. So because of my interest in engineering and physics, this seemed like an ideal thing for me. Actually, as a graduate student, my one cosmology course was taught by Sir Fred Hoyle. And philosophically, I really liked the steady state theory with no beginning and no end. However, he wasn't my advisor, actually. In my thesis, I used one of the two antennas of this first Owens Valley Interferometer to make a map of the Milky Way. Since dish antennas tend to pick up some ground radiation as well as what they're looking at in the sky, and that varies depending on how you aim it. What I did was point to the west of the Milky Way and let the Earth's rotation scan my beam through it. And in those days we didn't have computers, so there was a chart recorder and you would see the power go up and down. And then later I would take a meter stick, draw a line across the bottom, and measure above that. This was good enough for the Milky Way since it's very thin compared to its diameter, but it was clearly unsatisfying because here we are inside it, and nowhere we look would we have no Milky Way radiation. But there was nothing better I could do at that point. Meanwhile, at Bell Labs, John Pierce was a polymath who went around inspiring people to do things at Bell Labs. He wrote the book on electron guns to make electron beams. He contributed to communication theory. He started what I think was the first computer music project, and he wrote science fiction. I think probably the latter was the influence that made him think about putting a telephone repeater in orbit. Anyway, he wrote an article about this, and so when Sputnik went up and later NASA was planning to launch the Echo balloon, Bell Labs was ready to jump. He knew that the Echo balloon would not be a usable communication satellite, but it's always a good idea to start your experimentation with something fairly simple. So you use the very simple satellite and you learn how to track it. You'll probably learn a lot about what you have to know to do the more complicated thing. So they decided to put a big effort into that. Now we have a spherical balloon. When a wave comes up and hits it, it bounces off, it gets scattered in all directions. So the return signal was going to be very small. So they put together two Bell Labs inventions to make a very very sensitive receiving system. A traveling wave ruby maser, which had been actually built for the Cold War, and a large Horn-Reflector antenna. The Horn-Reflector would not pick up so much ground radiation that it overrode the maser's very low noise. So ECHO was launched. It was used as a microwave relay. Eisenhower's voice was transmitted from JPL, received at Crawford Hill on the 20-foot Horn-Reflector, and broadcast to the world over landlines. They had started Telstar. It was completed, launched in '62. The 20-foot horn was changed to receive one of the signals from Telstar. So after finishing my PhD, there had been a Caltech recruiter coming around our area, and I took a job at Bell Labs. Arno Penzias had been hired more than a year earlier. He had done a radio astronomy thesis with Charlie Towns at Columbia. He had actually built a maser. So why did Bell Labs hire 2 radio astronomers? Are we going to make communications better? Well, I think the reason they told the management is that radio astronomers know about large antennas. They know about measuring weak signals or receiving weak signals through the Earth's atmosphere. It would be good to have a couple around to help us with satellite communications. But I think there are 2 other undercurrents here. One is that the group I joined was the same group, some of the same people who had been at Bell Labs in the 1930s when Carl Jansky discovered, if that's the right word, radio astronomy. Carl Jansky had discovered that there were signals coming from the galactic center, and that was the start of radio astronomy. Now that was the time of the Depression. They were working on short hours. It seemed important to do Bell system business rather than follow up leads like that. I think they felt bad afterward that that lead had not been pursued and wanted to do so. In fact, my first boss had roomed with Carl Jansky when they were first together at Bell Labs. The other thing is that Art Crawford, my first boss, who had built the 20-foot Horn-Reflector, and the people who had made the maser were quite proud of what they'd done. And they wanted to see it be used for something more than just a passing satellite experiment. So they were happy to have a couple of astronomers around to actually make use of what they had done. The attraction to Arno and me was a very good research environment, generous support, and the opportunity to use the 20-foot Horn-Reflector with a very low noise amplifier, which would make this relatively small antenna quite sensitive. Both Arno and I had used larger antennas, but there were special properties of the 20-foot Horn-Reflector. This shows a picture of a few Horn-Reflectors the way they were originally used on a microwave repeater tower. A weak signal would come in from somewhere, be received by one of them, and then a strong signal transmitted out to the next tower, maybe 20 miles away. This is the 20-foot Horn-Reflector. It's been turned over on its side. And let's see if I can get the pointer to move around here. Can you see this? Yes. This is the reflector part, which is a piece of a paraboloid. So a wave coming in here is reflected down the horn and focused inside the cabin at the obvious place. You can see that there's shielding from the receiver all the way out to the reflector. And that does a very effective job of preventing ground radiation from getting into the receiver. The other wonderful thing about this antenna is that there's a large cabin out here which can support a lot of weight and doesn't move around with respect to gravity. So we could put very large receiving equipment in there. The maser itself must have weighed 1,000 pounds with its permanent magnet and all, and we put quite a bit of other stuff in there. So After I got there, Arno and I clearly were going to work together since there were two of us. And so we set down a little list of the things we thought we might want to do. The first was clear. We should measure the absolute strength of a radio source called CfA, which is the strongest in the sky, at 4 gigahertz. This would be useful for astronomy, and if we did it at 4 gigahertz, which was a satellite frequency, it could also be used to calibrate Earth station antennas. So it served the Bell system, and it was a service to astronomy. Then we would switch to about 1.4 gigahertz, which might include the hydrogen line, and we would look for a halo of radiation around the Milky Way and fix up Arno's thesis, which had been looking for hydrogen clusters of galaxies. By starting with a 4 gigahertz system, we could make a null measurement for the halo of radiation of the Milky Way. We built the best measuring system we could. Arno made a liquid helium-cooled reference noise source. We're measuring thermal noise, so we usually refer to it by temperature. The higher the temperature, the more noise there is. It's just the most convenient way. I made an accurate switch and a radiometer system for comparing them. After assembling our radiometer, the first measurement, as I've said, was a big disappointment. The antenna was hotter than it should have been by about 3.5 degrees. This same effect had been seen earlier at Bell Labs, but had been dismissed because it was within experimental error. But we had a direct contradiction. By this time, though, Dave Hogg and I had measured the gain of the 20-foot Horn-Reflector, and we didn't want to do anything to it until we had a chance to transfer that to celestial sources. So we spent 9 months improving our receiver, checking everything out, calibrating. And during that time, the 3.5K extra noise was always the same wherever we looked, unless we were looking at some specific source. During that time, we tried to think of everything we could to explain this extra noise, and we ruled out most of them. Since time's a little short, I'll talk about 2 of these things. There were a couple of pigeons living in the antenna. And we thought that pigeon droppings might actually make microwave radiation. They would absorb microwaves. So at some point we replaced the receiver with a pigeon trap, caught the pigeons, put them in a box, shipped them in the company mail as far away as we could, which was Whippany, New Jersey. We found the name of a pigeon fancier, sent them to him. He looked at them and said, "These are junk pigeons," and let them go. Well, what do you expect? 2 days later, pigeons are back. So, in the interest of science, our technician brought in a shotgun, and that was the end of the pigeons. Then Arno and I got up there in our lab coats with a broom and scrub brush and cleaned out the antenna. The other sort of unusual thing we thought about was that in 1962, there had been a high-altitude nuclear explosion out in the Pacific. I happened to be in Honolulu at the time, sort of celebrating my PhD, visiting my wife's sister, and the sky lit up like you wouldn't believe when this thing went off. It went off about sunset, but the sky just turned orange. David was talking about fantastic northern lights here. Well, you should have seen that. Northern lights on steroids. Anyway, it filled up the Van Allen belts, so we thought that was a possibility. But after a year, it hadn't changed, and those would have been decaying. Then one day, Arno called Bernie Burke, a fellow who now has been at MIT. And neither one of them remembers what the topic of the conversation was, but at the end, Bernie said, "What's going on with your crazy experiment?" Now, the background of that is that Arno and Bernie had been on an airplane going to Canada to some meeting, And Bernie had been saying, what are you guys going to be doing at Bell Labs? I think the implication, why aren't you at a real academic institution? Anyway, Arno had explained our plans, and Bernie had said, there's no halo in the galaxy. You're wasting your time. So anyway, Arno laid it on him in this conversation. We had this extra 3.5 degrees. We can't find it anywhere. And he said, you should talk to Bob Dickey at Princeton. So what was the background of that? We knew Dickey had been interested in gravity theory. What we didn't know was that he'd been thinking about a Big Bang. He was thinking about an oscillating Big Bang and that it would be very hot. And as it expanded, the radiation in it would cool off. And he did a lot of microwave work during the Second World War for the radar effort. And he understood that it would become microwaves. So what does a university professor do when he has an idea? He got himself 2 postdocs. He was at Princeton. He got 2 very good postdocs. Jim Peebles was set to calculating what would happen in a Big Bang, and Dave Wilkinson started building a receiver to look for the resultant radiation. So Jim finished his calculation. Someone at Johns Hopkins asked him to give a colloquium. He went to Dave and Bob Dickey and said, is it all right if I talk about my calculations? They say, yeah, we're so far ahead, no one could catch up with us. So he went off, gave the colloquium. A fellow named Ken Turner heard it. He was a good friend of Bernie Burke. He went back and told Bernie about it, and Arno happened to call the next day. So he told Arno about it. So Arno called Dickey, and it happened that the gravity group, as it was called, was having a sack lunch in Dickey's office. Phone rang. Dickey picked up the phone, started talking, and they heard atmospheric radiation, sky noise, antenna temperature, all the things they'd been thinking about. Their ears really pricked up. And after a few minutes, Dickey put the phone down and said, boys, we've been scooped. So we invited them over. They came over, and I think we were able to answer all of their questions about what might be right or wrong about our experiment. Arno and I were very happy to have any explanation at all at that point. However, we didn't take cosmology very seriously at that time. So we and Dickey's group wrote 2 separate papers. The short one you saw before about what we'd actually measured. We had previously published a much longer paper about the CfA measurement, which had all the details in it. And they wrote about the Big Bang and the noise that might be there. After one final check, we submitted our paper. But before the paper actually came out, Walter Sullivan was poking around the Astrophysical Journal office and got some hint of this. And he talked to us and the Princeton people and wrote a front page article in the New York Times on May 21st, 1965. That started me thinking that this cosmology business may have some real import. As a personal story, it happened that my father was visiting from Texas the night before. He had business in New Jersey, 3/4 of an hour away from where we were. I was still kind of a graduate student in thinking and got up sort of late, but he was a business guy and got up early. And he walked the 1/4 of a mile to the local drugstore, bought a New York Times, and came back. And there on the front page of the New York Times was our telescope and the article about the discovery. We were both very pleased, I think. So I'm here to tell you that these 2 guys in 1965 didn't know how big a thing they'd come across. It only came on later. I feel very lucky that I had the job at Bell Labs. Bell Labs supported us for taking Bell Labs technology and applying it to astrophysics. There were also many experts, people who had invented the things in microwaves that people used, who were there and were happy to answer questions. Another wonderful thing was I started my career when radio astronomy and cosmology were relatively young sciences, but poised to blossom as technology improved and people were able to measure more things. And at that time, partly thanks to Sputnik and partly thanks to what science had done during the Second World War, our nation was interested in supporting science and willing to spend the money to be the science and technological leader of the world. I was asked to convey the excitement of making the discovery. As you may have gathered from the talk, there was no aha moment in this discovery. There was a long period of trying to get to the bottom of our problem. The importance of the discovery really only became clear over time. It became clear as theory was developed and as receivers got better so that one could look farther into the background and see something more than just a completely featureless picture of this background. It's only the thing that Alan was talking about analyzing. However, it's been very satisfying to see all of this develop, to see the beautiful spectrum that Kobe produced. It's probably the world's best black-body spectrum, and the wonderful WMAP and now Planck pictures that Alan showed the analysis of. So, it's been a wonderful journey. Thank you.